Hello guys, and welcome to my talk about kinetic bombardment. So let's get to the talk right away actually. I am going to be talking about the kinetic bombardment, and the idea relies on something that is not new. The idea relies on destroying stuff with mass and gravity and speed, and that idea isn't new. I mean, there's a common misconception that it is possible to throw out a coin from the Empire State Building. The mass and the speed should kill you, which is of course not possible because of the drag. But another thing that do work is this projectile used in the Vietnam War. It's called the lazy dog bomb, and it is similarly sized of a normal pistol projectile. It is slightly denser and it also has fins, and the idea is to pack thousands of these in a box, fly above enemy territory, then throw out the box, and then a carpet of bullets will fly down on the enemies. Another weapon that is similar to our kinetic strike is the bunker buster. This is the first bunker buster called the Disney bomb, and the idea is similar. You need a lot of speed and some mass, and then the bunker buster will fly into the earth. And a bunker buster actually also carries some chemicals explosive, so it will explode once it has penetrated X amount of soil. If you still don't believe that mass, speed and gravity is very dangerous, then ask the dinosaurs what they think. Anyway, so let's define now what is this kinetic bombardment. And it is actually just giant metal telephone poles in space. Specifically, it is a satellite with a magazine of these metal poles, and the idea is a commander can command a strike, and the poles will then deorbit from the satellite and then be sent towards Earth, and of course the orbital velocity and the mass of the rod will result in a massive impact. Now, in addition, the rods also have a guidance system and some fins, so it can be controlled where it should land. Now, this idea was developed in the Cold War, where two superpowers was busy developing space stuff and weapons, but the Outer Space Treaty prohibited super weapons, or at least atomic weapons, in space. So this system is a way to bypass that. You know, of course it is possible, it is legal to have metal poles in space. It will work, but it was never carried out. But this system lives on in books, movies and games. Okay, so here is a picture from a game called Call of Duty Ghosts. So this is the satellite I was talking about. It carries a magazine and it can then fire down these rods. Another attempt of using this technology in a game is Tom Clancy's End, where we see the satellite. Now let me just quickly talk about some advantages of a kinetic strike. You know, they are easy to handle. They don't require some special weapon room, or some atomic weapons have a short half-life, so they will need to be refueled. There's nothing about that stuff here, it's just a metal rod. They are impossible to deflect once they are on its trajectory, because, you know, in a normal missile system you send up a counter rocket up to the incoming rocket, and this counter rocket will explode, and the fragments will then destroy either the chemicals, the fuse, or the guidance in this bomb. So that's how it takes out the bomb. But if a kinetic strike is coming, it has so much inertia you can't do anything to it. It will just fly down its own path and hit the target. And then it will take out anything, right, because it is so dense. The only defense is either moving fast or either being many meters underground. Then it is of course also mass producible. Should you suddenly need the technology, then the only thing you need to do is kind of like melt the poles, right? Then you can strike anywhere, anytime, depending on how many satellites you have orbiting Earth. The more satellites you have, the often you can strike anywhere. Okay, so let me show you a video of this technology used in a movie called G.I. Joe Retaliation.
Satellite 1A, we have remote launch authorization.
3, 2, 1, drop. A rod touches down 8 times faster than a bullet, and with a force significantly greater than a nuclear warhead. None of the fallout, all of the fun.
According to that movie, it is really powerful. And I know. Who doesn't love a good science fiction movie? I said a good science fiction movie. But is it realistic the way they portray these weapons? Was that powerful enough? We saw the London completely destroyed. Well, it has suddenly caused confused online. Here I'm showing you a screenshot. Side where you can ask question, is an orbital kinetic bombardment considered a weapon of mass destruction? Well, it is suddenly a weapon of mass destruction. Get it? So this was sort of my introduction to the topic, and now I'd like to find out if we actually have the energy of a tactical nuclear weapon. So we'll try to find the impact energy. Then I'll talk about bombardment type, what kind of penetration and what kind of impact would we expect when this strike hits, because we saw, of course, in the video that that London was destroyed by an earthquake, kind of. Others are confused, is it as strong as atomic weapon? Well, of course, it does not explode as an atomic weapon, it will not explode radially, right? So let me make a calculation. At first, I'd like to do a quick and easy calculation, so I'll need to find some data on this rod. And luckily for me, the technology has been discussed, and in one paper, the Air Force Transformation Flight Plan, they discussed the technology, and they suggested the rod should be made of tungsten. And of course, that's a really dense material, almost 20 grams per cubic centimeter. And in the paper, they suggested that the height should be 6.1 meters and a diameter of 0.3 meters. Plug it into the volume of a cylinder, and we get out the mass of one rod, 8.3 tons. Now, I'd like to point out why we use tungsten. And it is, of course, because it is really dense, but also when you are entering the atmosphere really fast, you will have a quite high entry temperature, according to NASA, 2000 degrees. And by the way, there's a common misconception on why this happened. People think it's because of air friction, but no, actually not. It's because it's have a lot in common with a diesel engine. So here we have something that should resemble a diesel engine, where we have some gas and a piston. And a diesel engine will suddenly compress the gas, and this gas happens so fast it does not have time to torque and distribute the heat in the engine, and so the result is the gas getting really hot in no time and explodes. And that's called the adiabatic process, and that is of course why we heat up our entering objects, because it is compromising the air in front of it really fast. Now, normally you can use a depleted uranium to make your projectile. It has been used in tank rounds, for example, but depleted uranium has a melting point of 1100 degrees Celsius, and so it will melt if you send it down the atmosphere, so it won't work. Tungsten, or wolfram, of course, is known for being not only extremely dense, but also have extremely high melting point of 3500 degrees. So that's why we use tungsten. Okay, so now I'll need to find an orbital velocity. If I had to construct the rod, then I would put it in low Earth orbit of 400 kilometers, as the International Space Station is. Because if we are in low Earth orbital, well, then we are traveling the Earth many times a day. Of course, we have high speeds because we are in orbit, but we also have significantly low drag. Okay, so now let's find the velocital speed. So our satellite, of course, has some velocity traveling around the Earth, and we can use the Vis-Viva equation if we have assumed the orbital is circular, sorry. And we'll have to remember that first of all, the m is in here is the mass of the Earth. R is the distance from the Earth out to the satellite. So this whole r, Earth plus the height of the satellite. If I select the velocity, we can easily find the speed, 7.66 kilometers per second. Now we are ready to make our back of the envelope quick calculation of the impact energy, because we know these parameters for the total energy. So we know the kinetic, right? We know the mass and the velocity now. But this is a really quick calculation, and it comes with some assumptions, some crazy assumptions. That it comes with the idea that friction does not exist. Of course, we're flying through atmosphere and it will take some energy. We'll also assume that the acceleration g is g everywhere. And we also told we're on orbit, and I'll assume that suddenly the orbital velocity will be pointed towards Earth. So the satellite will just go like this with the orbital velocity. So now we're ready to plug in our numbers, and I get this amount of joule, which is equivalent to 63.7 tons of TNT, and 1 ton TNT is defined like this. So is it atomic weapon? Well, it will be the equivalent of 0.5% of 15 kilotons TNT, which is the atomic weapon Little Boy used in Hiroshima. So not quite. Or is it? Because the energy is actually quite similar to the David Crockett atomic weapon. It's the atomic weapon here, It is the smallest weapon, nuclear weapon ever made, only consisting of 20 tons TNT. And of course, and according to my calculation, we had 63.7 tons TNT available. So let's see how much destruction 60 tons TNT is as an atomic weapon. So this is the energy our kinetic strike would have in our assumption, but let's just say that now it's not a kinetic strike, but now it's an atomic weapon instead. So what will the destruction be? Well, here we are in nuke map, and we are above my city Aarhus, and we can simulate an atomic bomb, and I'll do that at an atomic bomb of 60 tons TNT. And what do we see? Well, we see in here, we see a fireball radius where everything will be vaporized. Then we see this outer circle here, 3rd degree burn. And then we see a high overpressure zone here where buildings are likely to collapse. A green zone here where you can expect a fatal dose of radiation. And then a light blast damage radius where windows are likely to shatter. So it was not a super weapon, but it's still really, really strong. So now I would like to find a better calculation for these impact energies. And to do that, I want to build a simulation. And the first thing we need to do, so I will need to fix my assumptions in order to do a good calculation or simulation of this impact energy. And the first thing I'd like to fix is the orbital energy, because we assumed before that we were in orbit and then suddenly we changed our trajectory down into the Earth. So here we see the Earth, and we see our rod in orbit, and let me just show you a quick video of that. So the idea is now we need to find some value that we can subtract the velocity of our rod with, such that gravity will take over. You see it's orbiting slower and slower and slower here in this video, and suddenly we hit the Earth here because we are traveling too slow and gravity is too strong. So what can we do in order to find the equation for that? Well, we can start with the equation. We can start with the equation from before, the orbital velocity. And if we subtract the velocity in a short amount of time, we can work with infinitesimal, so we can differentiate. So let's do that, differentiate with respect to r. And this works because v also depends on r. Let's only carry out this differentiation here on the right hand side. Of course, we obtain this new equation. If I then forget about this equation in the middle, and then I know this thing here is equal to this thing here, and so I'll use it to isolate dr. Now I don't like the square root of gm, so I will just isolate that in this equation up here, stuck that in, and now I obtained finally this equation. And we have to remember that this only works if we break shortly, so that's why it's dr and dv, but I'll just call it delta r and delta v, and we'll remember that it only works when we break fast. So what can I see with this equation? Well, I can see that if I apply a delta v, a difference of velocity of 239 meters per second, the radius of orbit will be decreased by 400 kilometers. That was, of course, the height we were orbiting in low Earth orbit. So now we know the actual velocity we're starting with, and I'll call it the drop velocity. So it's the orbital velocity minus this delta v we need to subtract in order to collide with Earth. So I'll just do that here. So the new drop velocity is 7.42 kilometers per second. And now my life got easier in my simulation, because before we were orbiting around the Earth and we would like to hit the Earth, of course. But my idea is now that instead of being in a circular orbit around Earth, I'll just assume that we are falling straight down with velocity, what I call the drop velocity, the one we just found out. Because we are slowly approaching the atmosphere, and once we are in our atmosphere, we can then use the fins of the projectile to fly straight down, and the velocity we are falling straight down with will of course be the drop velocity we found. Okay, so now our object is falling down, it's being attracted gravitationally, but it is also being stopped with the drag force, of course. That's the next step in order to carry out my simulation. We're still on our path to do a better calculation of the impact energy than just my assumption, and I want to do that with a simulation. And the last step I need to do in order to carry out the simulation is finding the drag on the object. So we know that air friction is not a fun size actually, because if you shape your wings in some way, then suddenly the drag force the air friction will cause lift and you can suddenly fly in a big plane, but we will only look at it as a stopping force in the opposite direction of velocity. And in general, the you can look at it as either being a linear term, so some constant b times the velocity, or a quadratic term, so some constant c times the velocity. And we will use that approach as well. So what drag regime are we in? Are we in the linear or the quadratic regime? Well, a way to determine that is using the Reynolds number, which is the inertial forces divided by the viscous forces. And the viscous forces, of course, you know that is how hard it is to push against something in the slow regime. So say you're pushing a ball through honey, some dense liquid, then it is actually quite hard to do it. That's the reason, because of the high viscosity. And that viscosity, the viscous forces, is what's responsible for the linear drag, because say you want to push the ball the double amount of distance in the honey, then you'll also need to push the ball against double as much honey, right? So that's why the linear term is responsible for the viscous forces. Now the inertial forces are responsible for the quadratic forces, and that is when you have if you're on a high speed flow. So the molecules overlapping structure really doesn't matter as much, because you're flying so fast, causing this turbulent flow, and so it must depend of the inertial of all the particles you are kind of throwing in a random direction. Yeah, so that's why it's called the inertial forces. And of course we are flying really fast, so we must have a really high Reynolds number. We must expect a flow like this in the turbulent flow. And one equation that wants to map that is the drag force here. It is half times the density, so we need to find that. And the velocity, we know that. And the coefficient of drag, which we'll talk about in a second. And then the area as well. And the area can be calculated easily, and that is actually why we are using tungsten as well. Because if you have a higher density material, then you can pack more in a smaller area to obtain a higher mass. Okay, so now we are almost ready to carry out our simulation. We only need to talk about the coefficient of drag and find the density. So that's our goal now. And generally the drag coefficient is just something that tells you how does the object stop you. I mean, how much will the object be resistant to flying? That of course depends on a lot of things. It depends on the skin of the object, it depends on the geometry as well. So it is really not a fun size, and it's hard to obtain. So either you do it with some crazy approximations, you do it in a wind tunnel, or you do a simulation. And I'll just find it by looking at this table here. This is a table I found of high velocity moving objects, and I even found a cylinder. So here they're saying speed in Mach number, which is of course the speed of sound. So here we have the speed of sound, here we have double the speed of sound, here we have 3 times, and on the y-axis we have the coefficient of drag. If the system was actually carried out, no one in their right mind would actually use the coefficient of drag of the circular cylinder, because the coefficient is just way too high. So they will probably make it sharp and pointy, right, to reduce the drag. So I'll do that as well. Yeah, I'll just pick a constant value of 0.5 as this figure suggests. So now we only need one thing. We only need the density to talk about the actual impact. And of course the density of air, and of course that must vary with height. And I can find that if I use this barometric equation here. It maps the pressure on the atmosphere and different heights, and then I use the ideal gas law to find the density, and then put that pressure in there that depends on the height. And so I get this density depending on the height, and it turns out it looks really weird, doesn't it? And that's because this equation of pressure is only precise to around 100 kilometers. That's why it looks so crazy low up here, but it is actually the regime that it is important that the equation is precise, because below 100 kilometers, that's where the drag really works. It doesn't really do a lot of work in the higher higher altitude. The drag is sufficiently low there. So now we're ready to carry out my simulation, and this is finally the result. And so my graph is showing we start at 4 kilometers of height, and then we drop the rod down to 0 kilometers of height above Earth. Then it is also showing the speed of the different altitudes. So of course we start at the drop speed right here, and then as time flies, as we are dropping, we are gaining more and more speeds, because there's no drag, there's only the initial speed and then the gravitational attraction. Then we suddenly hit some serious air force, and so now I just look at my final velocity. It's not 0 down here, by the way. The y-axis is not 0 down here. So I can just look. It's around 6,951 meters per second. Then the only energy now is the kinetic energy. I can plug that in, convert it to tons of TNT, and it's 47.7 tons TNT. And we also lost a lot of energy due to the drag force as expected. Okay, so now I would like to talk about bombardment type, because in the video we saw like total destruction, but what destruction and what kind of impact can we expect? And actually the projectile have a lot to do with a dart actually, because a dart has a really high sectional density, which is the mass divided by the area. That's called the sectional density. And if that sectional density is high, then the object is really good at penetrating stuff. A dart is really good because it is quite heavy. It's actually, fun fact, it's actually made of tungsten, and it has a really small impact area. So the sectional density is very high, and it's really good at impacting stuff. What kind of impact zones are we in? Are we in rigid, hydrodynamic, or what? And I found this paper here, long rod penetration transition zone. And here we see a figure that's really important for the paper. That's the main point. At the x-axis we have velocity of impact, and the y-axis we have penetration depth divided by mass. And what the paper finds is that we have a zone here where what's called the rigid zone, where throwing the stuff faster would result in a deeper penetration. Then at zone 2, suddenly the penetration drops. And that's because we have transitioned from what they call the rigid zone to another zone where the rod will start deforming. So just from a car is designed to crumble when it impacts something such that it absorbs all the kinetic energy. And that's what's happening here. If you throw the object hard enough, it will start to crumble. Then at higher and higher velocity, we see higher and higher impact depths again. Because we're throwing so hard, it does not matter. We are losing some energies to this crumble. There's just so much energy available. And more importantly, the paper claims that we are reaching a steady value at really high speed. So it should be steady at some value. And here we see a simulation from this book here, Armor Materials Theory and Design. So we have some rod. I actually think it's a tungsten rod in his simulation, and it's impacting a steel target. What we see is we have so much, by the way, I forgot to mention, we are in a hydrodynamic penetration zone because we are flying so fast, 7,000 meters per second, right? So that's the penetration speed we have. So we are in this zone here. And what we can see in this figure is that we are just flying so fast that everything will be completely melted or vaporized. And actually it doesn't matter how strong the object is that we are hitting. We have so much pressure it will destroy everything we hit. So this is a figure that's mapping out the pressure as a function of time. And first we hear regime 1, which is called the transient zone. And that's the initial impact where we see a sudden spike in pressure because we are starting to impact. Then as time evolves, then we go into the primary zone here, and that's actually figure 2, 3, and 4, where we are eroding the object, where the object is being destroyed. And actually, funny enough, the pressure is constant in this zone, and the velocity is also constant in this zone. And that's because we are traveling so fast, there's no time to send out the disturbance pressure. So we're just flying straight towards as if the end didn't hit the steel target yet. Then when the rod has eroded, then there's a secondary zone here where actually even though the rod is eroded, it still carries some kinetic energy. And lastly, there's a recovery zone, which is not important according to the book, so we'll ignore that as well. Let me find out the maximum impact depth, because the paper stated that there's a theoretical upper limit on how deep you can go. And let's find that, by the way. So here we see our rod penetrating a target. It has a length. Our projectile, of course, has a density, and then we have the target density. The tail of the jet the tail of the target is flying with speed v. The stagnation point, or the point of impact, is flying with speed u. It's flying a little slower because it is in the process of impacting. Now let's do something. Let's change coordinate system to our stagnation zone, to our impact zone. So now our coordinate system is in this point here. So with respect to that point here, the tail is now impacting with speed v minus u, the target is flying up to the stagnation point with speed u. Then we can use this equation here. This is the Bernoulli equation, which says this point of stagnation, that's where the pressure should be equal. So we can set in our pressure zones here. We know they should be equal according to that equation, or the Bernoulli's equation. It turns out I'll later need V minus U, so I will isolate that in this equation. Because we earlier found out the penetration is in constant speed, we can use the simple equation here to find the time of impact, how long time it takes to impact. The maximal penetration length should then be U times T, and then combine these two equations to get this equation here, and then I'll put in V minus U down here. So it's the maximum penetration length, L, is given by the length of the rod times the square root of density of impact divided by the density of the target. And it turns out we can multiply by 2 here to obtain a better equation. That's because of the inertia that the projectile has, even though it is completely eroded away, then it still carries some kinetic energy. Okay, so let's use that equation to see how deep a kinetic strike will penetrate soil. Soil has a density of 1.8 grams per cubic centimeter. Let's plug that in our equation. We of course had rod was 6.1 meters and the head has a density of Wolfram. And so our model predicts that our impact depth will be around 30 meters. And most bunker busters can only do 12 meters in soil. And actually talking about bunker buster, let me talk about this biggest bunker buster ever made, the Moab. The Moab, almost the same dimension as our kinetic strike. And the kinetic strike had these values. So it is actually almost the same size. And I have a video of impact of this missile. So here we see the gigantic missile being dropped. And here we see it impacting the soil. And what I want to show you with this, of course, first of all, a bunker buster also carries some chemical explosive. So it will go off. Of course, our kinetic strike will not do that. But what we see here is that most of the energy is actually just being dissipated into the ground. We don't see a big crater or something. The missile kind of just disappears into the ground. And so most of the energy must be dissipated into the ground, because our kinetic strike is traveling much faster than this Moab. So maybe the sonic boom or maybe some fragments will be dangerous, or maybe the plasma around the fast moving object will be dangerous. But it seems like most of the energy is just being dissipated into the ground. So let me now quickly talk about earthquake and asteroids, because in the video we saw on the start, we saw the kinetic strike completely destroying London. So that destruction must be similar to a really strong earthquake. One example could be the 2011 Tohoku earthquakes, where a whole city was completely destroyed. So I think these energies are quite similar. And by the way, that's the earthquake that had the accident of Fukushima. The magnitude of the earthquake was 9 on the Richter scale, and it had only the surface energy, so we're ignoring all the ground energy, had an energy of 1.7 times 10 to the 17 joules. And if we wanted to have as much energy with a tungsten rod, our tungsten rod will need to be 10 million tons. Have a mass of 10 million tons tungsten. So that's crazy. We will never get that kind of destruction. If you take a look at how much energy we actually have, from our simulation, and then the kinetic strike energy will only have a Richter scale of 4.4. And according to this figure of different Richter scales, then we should expect nothing less than a light earthquake and no destruction, just some lamps wiggling back and forth. It's not like 0.9 of the Richter scale where we see the whole city being destroyed. So that's not realistic. And I want to talk about asteroids, but it turns out they are not representable for a kinetic strike. Because according to this paper, if the asteroids are under some critical diameter called, the critical DC, if it's under 100 meters, then it turns out the asteroid will just be eaten up by the atmosphere. But if it is above 100 meters, then it will hit the Earth, but the asteroid will be way too strong for our kinetic strike. So it doesn't make any sense to talk about asteroid in my talk. But I still talked about it because I think when you're expecting a strong kinetic strike, maybe you're expecting a big crater like this. but you'll only see an extremely big crater like this because the asteroids are really big, much bigger than our kinetic strike, and also they are spherically formed, so they won't dig themselves into a really small area as they would do with a cylinder. They are just some fat spheres. Okay, so let me now discuss why kinetic strike didn't work out. It takes massive energy to put just one rod in orbit, and just sending the rocket up, not even worrying about putting it into orbit, actually cost $3.7 million. No, sorry, $8 million. I want to say that the Moab we saw earlier, a bunker buster that is just as powerful, I guess, cost only $3.7 million. So, but of course the prices are declining, but it's still way too expensive. It is really easy to defend against. If you are enemy with some superpower, you can just, before they send down the rocket, you can just send a bucket of sand into the satellite, and the velocity will just completely destroy the satellite. And so a drone with a bunker buster is basically the same anyway, and it's much cheaper. So let me conclude. Kinetic strike is not a weapon of mass destruction. It is still very powerful though, but it has more in familiarity with a bunker buster where all the energy is being dissipated in the ground. And in order to be some supersized weapon of mass destruction, we'll need it to be an asteroid size. So I hope you found this talk interesting. If you have any questions, let me know below. I know it wasn't some fine polished animation as I usually do, but I still hope that you found it interesting. Thank you very much for listening.